Okay, this is AP, AB, and BC Calculus. We're doing Unit 3, Section 5, which is selecting procedures for calculating derivatives. So in this situation, we're just going to do a lot of practice problems. There's no new material in Section 5 of Unit 3. This is just a lot of practice of when you look at a problem, how do you figure out what is required to differentiate. So for all of these problems, I would suggest that when you see the problem pop up on the screen, you pause me first and try the problem and see how you do. And then if you get stuck, you unpause me and listen to a little bit of what I do, and then pause me again and try and figure out the rest of the problem, okay? So I believe I have 18 of these, so I'm just going to walk through 18 practice problems in this video. You are welcome to pause me as needed to try the problems. You're welcome to skip problems that you feel like you're really awesome at, but I would suggest that you make sure you can do all 18 of these problems. Cool. So P1, identify all of the following functions that would require the product rule for differentiation. So you're not differentiating, you're just identifying which ones would require the product rule, right? So, and again, I'd notice that the word require, right? So be careful here. So could I use the product rule on this one? Yes, right? So I could use it as U and V, but it's not required, because the smarter play here would be to distribute, right? To do 2x cubed plus 6x to the fifth, right? And now it's not a product, okay? For the second one, it is not required, right? It's not even applicable, right? This is not a product, right? For this one, yes, I would have to do the product rule. There's no way to simplify this. And for this one, yes, again, there's no way to simplify this. So product rule is required for these two, but not these two. You could use the product rule to find f prime, but it wouldn't be required, right? In terms of which one's actually required to use the product rule that can't be simplified, it's just h and k, right? All right, P2. So identify which of the following would require the quotient rule and justify your answer. So this one can be simplified, right? I could split this up into an x cubed over x plus a 3x squared over x plus a 5x over x minus a 2 over x. And now it's suddenly not a quotient rule problem, right? So plus 3x plus 5 minus a 2x, the negative first. It is not a quotient anymore, right? So now I don't need the quotient rule to do this. Now I could use the quotient rule to do this, but I don't need it, right? For this one, I do have a low function, I do have a high function, and there's no way to simplify them. So yes, I would be required to use the quotient rule here, right? For this one, I have a high function, I have a low function. Yes, I'm required to use the quotient rule here. And then for this one, I could rewrite it as a 5x to the negative third, so it is not a quotient anymore, so I don't need to use it. So that's not to say you couldn't use the quotient rule in all four of these. It's to say that these two require that you use it. Now there is a slight caveat to that. If any of you have been getting help on the Khan Academy, Khan Academy doesn't use quotients. So Khan Academy doesn't use low d high minus high d low, draw the line, square the low, pretty much at all. What they do is they take every single quotient they give you and they turn it into a product in a chain rule. So they would write this as 3x squared plus 5 times the quantity 2x minus 1 to the negative first, where this is your u and that's your v, and they do a product. I don't like this. You are welcome to do it, right? But they turn every quotient into a product and a chain, right? So I don't like that. I think that the quotient rule is easier, but certainly, so if any of you have been doing a lot of stuff on the Khan Academy, and if any of you are like, hey, none of them would require the quotient rule because I could cheat and make it a product, you technically can. I would not advocate for that, but it is technically possible. All right, identify all of the following that would require the chain rule, meaning a function inside your function. Well, this one is definitely a chain, right? It's a sign with a 5x on the inside of the sign, and that entire sign is inside a squared. So that is definitely a chain, right? Same thing here. I have a function inside my function, right? This is e to the 2x plus 5. 2x plus 5 is the inside function. This is my outside function. This is also definitely a chain, right? Now here, this looks like a chain, but I'm going to argue that it would make way more sense logically to distribute that cube power and make this a 27x cubed, and so now it's not a chain. So while you technically could use this as a chain, right, it doesn't necessarily make sense to do it. And notice that this one only has an x on the side, so this one is, or on the inside, so this is also not a chain. So the only two that require the chain rule are the first two. Again, it's when there's a function in your function. All right, so let's go ahead and dig into actually differentiating now. So here's P4. Again, if you want to do this without me, you should pause me, right? So I'm going to rewrite this, recognizing that the squared is actually the outside function. So there's actually 3 layers to this function, right? There's the squared, right? That's my outside function, right? And then there's the sine, which is my middle function. And then there's the 5x, which is my inside function, and that's usually the thing that has the x, right? So when I differentiate, I'm going to do the derivative of the outside, which would be 2 stuff to the first, right? And the stuff is a sine of 5x. So that's the derivative of the outside. Oh, hey, I did something stupid. I specifically have told you numerous times that you should never say that the original equals the derivative. Ignore that. Wasn't paying attention. So f prime of x. Okay, so I did the derivative of the outside. Sorry, I got so busy color coding that I did something stupid. So this is the derivative of the outside, right? Times, I used green for the middle. The derivative of the middle function, derivative of sine, is cosine of the stuff, right? So that's the derivative of the middle, right? Notice that I'm multiplying them. And then finally, the derivative of the inside would be a 5, right? That's the derivative of the inside. So when I clean this up, my f prime of x should be I think there's a 10 in the front, right? And it's sine of 5x cosine of 5x. And that's my answer. Now, if the AP wanted to be super duper tricky, just to throw this out there, if this were multiple choice, right? If it were multiple choice, the AP is tricky and will sometimes out of nowhere throw a random trig identity just to screw with you. So the sine of 2 theta is 2 sine theta cosine theta. So if they really wanted to mess with you here, they could rewrite this as a 5 times a 2 sine of 5x cosine of 5x, right? They could just make it like that. And notice that this pattern is the same as this. So they could rewrite this as a 5 times the sine of 10x. And that would be another possible answer. This is the same answer, but it's simplified using trig identities. So again, just to throw out, if the AP ever gives you a multiple choice question and you are sure you did this right and you don't see this answer, take a deep breath and calm down and think, is there a random trig identity or random previous knowledge that they could throw at me that would make this harder to spot? So this is the same answer, but again, it's hard to spot that. All right. Again, go ahead and pause me if you want, right? So this is definitely a product. There's my u and my v, but inside my v there is a chain because there's an e to the x inside my tangent x, right? So I'm going to start by going ahead and setting my product rule, right? So my product rule is u, which means just copy u exactly as it is, dv, which is totally going to be the thing that has that chain, right? So u dv is going to be the derivative of tangent, which is secant squared of stuff, times the derivative of the stuff, plus v, which was just tangent of e to the x, du, which will be a 2x. So when I clean this up, it's going to look like this. I'll probably put x squared e to the x at the front of the secant squared of e to the x, and then plus a 2x tangent of e to the x. And that's my answer. All right, moving on. Okay, same thing. So we're finding dy dx, and this is going to be implicit, right? It's not doable to solve this for y, and even if it was doable, it certainly wouldn't be worth it. Okay, so couple things to notice. In here, right, inside my sign, there's going to be a product, right? So when I differentiate my y to the 5th, I'm going to get 5y to the 4th, but I just differentiated y stuff, so I'm going to write a dy dx, right? Plus, now I'm going to differentiate sine of xy. Well, the derivative of sine is cosine of the stuff, right? But I have to times by the derivative of the stuff, and this is going to be that product, right? So the derivative of the stuff is going to be u dv, which would be dy dx because I differentiated y stuff, plus v du, which is just a 1 because you just differentiated an x. On the other side of the equal sign, the derivative of cosine is negative sine of the stuff times I need to differentiate the stuff, and I'll get 4y dy dx. Okay, so this is pretty ugly, right? My first suggestion is that you're going to want to distribute this cosine xy because some of it goes to a dy dx and some of it doesn't. So I'm going to get a 5y to the 4th dy dx plus an x cosine of xy times a dy dx plus a y cosine of xy, no dy dx there, equals a negative 4y sine of 2y squared dy dx. Okay, so now what I want to do, since I'm trying to solve for dy dx, is I want all the dy dx's on one side. It's up to you which side you move them to. I'm going to make the argument that if I just move this guy over here and this guy over here, if I just add or subtract accordingly to move them, that I'm going to get all the dy dx's on my left-hand side. So I'm going to get a 5y to the 4th dy dx plus an x cosine of xy dy dx plus a 4y sine of 2y squared dy dx equals a negative y cosine of xy, which was the only thing without a dy dx. So now I'm going to factor out this dy dx, because there's a GCF of dy dx in all of them, and I'm going to go ahead and scroll down and get myself a little bit more room. When I factor out that dy dx, I'm going to be left with a 5y to the 4th plus an x cosine of xy plus a 4y sine of 2y squared, and that's going to equal negative y cosine of xy. Then I divide that entire thing over, and I'm going to get that my dy dx is equal to negative y cosine of xy over 5y to the 4th plus x cosine of xy plus 4y sine of 2y squared. Okay, so that's all fine. If you had gone the other direction and moved, instead of doing the flip-flop I did up here where I moved this to the right-hand side and the other thing to the left-hand side, if you'd gone the other direction, you'd get exactly the same answer but with opposite signs. So the top would be positive. You'd get y cosine of xy, and then every sign on the bottom would have come out negative. So negative y, 5y to the 4th minus x cosine of xy minus 4y sine of 2y squared. Okay, so again, same answer. It just depends on which side you added them to. It's not a big deal. Okay, that was a long problem. All right, P7. So in P7, you could use the product rule, but it is smarter to distribute, right? So I'm going to make this a 2x to the 3rd plus a 6x to the 5th. That's not calculus, and then my derivative is just going to be 6x to the 2nd plus 30x to the 4th, and that's it. If you'd gone the other direction, right, it's not wrong to do it as a product rule, so this is good. It's not wrong to do it as a product rule, right, if you did 2x squared as your u and you did x plus 3x cubed as your v. It's not wrong to do the product rule, it's just harder. So u dv would be a 1 plus 9x squared, right, plus v, which is this whole ugly mess, du would be a 4x. And then when you distribute, you'd get 2x squared plus 18x to the 4th plus 4x squared plus 12x to the 4th, which is going to give you a 6x squared plus a 30x to the 4th, which is totally the same answer but a lot more work. All right, P8 is hopefully pretty straightforward. This is just a polynomial. It's just a bunch of sum and differences, so you just differentiate each individual piece, right? So I'm going to get 7x to the 6th plus 6x to the 1st plus 0. So we're going to write it as 7x to the 6th plus 6x. All right, P9 is going to be a product rule, right? So you'll notice a lot of these are coming up from the previous first couple problems where I asked you to identify which ones you needed as a product, etc., rather. U, so it's u, dv, which will be e to the x, plus v, which is e to the x, du, which is going to be a 3x squared, right? So I'm going to get x cubed e to the x plus 3x squared e to the x, and that answer is great. This is the kind of thing that someday you might be asked to find the zeros for this. So it's also okay to notice that there's a GCF of an x squared e to the x, and that's definitely fine as well, right? So this is also totally fine. All right. We have another product rule here, right? So k prime of x equals u dv plus v du. Notice that 2x is not inside the sign, so I'm going to write this as an x squared cosine of x plus 2x sine of x, and that's great. If you wanted to factor out a GCF of x, you certainly could. I don't think it's really going to help you much here, but you certainly can, right? That's also fine. All right, moving on. Okay, so this is that one that we saw earlier that we can simplify. You could do it as a quotient. I would not recommend doing it as a quotient. So I would recommend that you simplify it first because that denominator is a monomial, so I can simplify. And so before I differentiate, so this is still not calculus, I get x squared plus 3x plus 5 minus a 2x to the negative first, which means now when I do calculus, now when I differentiate, I'm going to get a 2x plus 3 plus a 0, and then this will become a plus 2x to the negative second, so the answer you are likely to see is 2x plus 3 plus 2 over x squared. That's what you'll probably see if you needed to make this a common denominator, like if you were asked to do something with this, you might make them all have a common denominator of x squared, which would make this a 2x cubed over x squared plus a 3x squared plus a 2, and they would all be over x squared. So that's also fine. Same answer. Okay, so this is definitely one where I have to use the quotient rule, right? We saw this when we were doing the first couple problems, right? So g prime of x is going to be low. D high is going to be the derivative of sine, which is cosine, plus the derivative of cosine, which is a negative sign, okay, minus high, which is sine of x plus cosine x, d low, which is just a 1, draw the line, square the low, right? That's a minus, my bad. Okay, so that answer's fine, but you're likely to see it at least somewhat simplified, so you're probably going to FOIL this out, right? So when you FOIL this, you're going to get that this answer is, so first would be negative x, positive x cosine x. Sorry, my brain is slow today. It is too early and there has not been enough coffee. So first would be x cosine x. Outer would be minus x sine of x. Inner would be minus a 2 cosine of x. And last would be plus a 2 sine of x. And then when I distribute this negative, I'm going to get a minus sine of x minus cosine of x. And then you're not going to do anything with the bottom. You're just going to leave it as an x minus 2 quantity squared because it's already factored and simplified, and that's the best you can get. So when I combine my like terms, it seems to me that I get that this is an x cosine of x minus an x sine of x, which cannot be combined. I have negative 3 cosine of x and a plus sine of x, and that's the best I get. You're not going to be asked to do anything with this. It was mostly just a matter of differentiating, and that's as nice as it gets. All right. We have another quotient rule here, right? I can't simplify this. I have a high function and a low function, so my h prime of x is going to be low, d high, which should be a 6x, minus high, which is the 3x squared plus 5, d low, which will be a 2. Notice all these binomials are in parentheses, right? Square the low. So I just write that on the bottom. So when I distribute on the top, I'm going to distribute this, and I'm going to distribute the negative 2. So I get that this is 12x squared minus 6x, right? And then here I'm distributing not only the negative, but also the 2. So I'm going to get a minus 6x squared minus 10, all over a 2x minus 1 quantity squared. When I combine my like terms, I have a 12x squared minus a 6x squared, so that's a 6x squared, and I have a minus 6x and a minus 10 over a 2x minus 1 quantity squared. And that's about as good as it gets. You could take a GCF of 2 out of the top if you want. It doesn't make your life significantly better. All right, we saw earlier that the smartest thing to do here is to rewrite this as a 5x to the negative third. You could actually treat it as a quotient rule, but the numerator is a constant, so when you do that, dh, like d high, just goes away. So my k prime of x is going to be a negative 15x to the negative fourth, so you're probably going to see it as a negative 15 over an x to the fourth. Certainly, again, you could do it as a quotient rule. I promise you, if you did do this as a quotient rule, you get the same answer, right? If I did this as a quotient rule, I would have low d high minus high d low. Draw the line, square the low. Right, I'm going to get a negative 15x squared on the top and an x to the sixth on the bottom. And sure enough, that simplifies to a negative 15 over x to the negative fourth. All right, so we have a chain, right? There's a function inside my function here. So my g prime of x is going to be the derivative of the outside, which is e to the stuff, times the derivative of the stuff. So I'm going to see this as a 2e to the 2x plus 5. And that's it. Okay, so here, you could technically do this as a chain rule, but as we saw early in this video, I would suggest that you simplify it by distributing that cubed onto the 3 and the x. So my h prime of x is going to be a 10x plus 81x squared, right? And that's fine. If you did it the other way, if you did it as a chain rule, right, So if you took your h as a 5x squared and then this was a function inside a function, it's going to work. It's just going to be a little harder, I think. So this is still going to be a 10x, right? But this one, when you differentiate stuff cubed, you're going to get 3 stuff to the second times the derivative of the stuff. And if you clean that up, here you still have that 10x, but here you have a 3 times a 9x squared times a 3, which is totally an 81x squared. So it's the same thing. All right, so here we have a quotient rule. Now, this is one of those times that the Khan Academy's tendency to flip things up is actually not awful here if you wanted to make this a product. So I'm going to walk you through 2 different ways to do this one. If we do this, what I would consider the most logical way, which is to use a quotient rule, my f prime of x is going to be low d high minus high. D low is going to involve a chain, right, because there's a 5x inside that e, so e to the stuff times the derivative of the stuff. Draw the line, square the low, and so what I'm going to end up getting if I do it this way is a 3x squared e to the 5x minus a 5x cubed e to the 5x over an e to the 10x. I can factor out of the top an e to the 5x, which would cancel from the bottom. So this answer is not wrong, but if I wanted on the top, I could factor out an x squared and an e to the 5x. If I did that, I'd be left with a 3 minus 5x, right? And I can cancel some of my e's on the top and bottom and make this an e to the 5x. So one way you might see this is as an x squared times a 3 minus 5x all over an e to the 5x. That's great. This answer was still totally right? This answer was totally right. If you chose to do this the other way, so I don't advocate for the changing things into a product, but if you chose to, you could rewrite this as an x cubed and an e to the negative 5x and then do it as a product rule, right? Again, I don't normally advocate for this, but it is an option technically, right? So if you did that, you'd have u, dv is going to be an e to the negative 5x times a negative 5, right? Plus v, which would be e to the negative 5x, du, which is a 3x squared. So if you did this, you're going to get that this is a negative 5x cubed over an e to the 5x plus a 3x squared over an e to the 5x, which if you put this stuff together, you're going to get a negative 5x cubed plus 3x squared over e to the 5x, and I assure you if you factor out a negative, or if you factor out an x squared, you get the same answer, right? If you take out an x squared GCF, you get negative 5x plus 3 on top of that e to the 5x, and that is definitely the same answer. So, okay, for the last problem, we're asked to find dy dx in a situation that looks as though it's set up to be implicit. I do want to show you that you can do either implicit or explicit differentiation here, and I want to explain to you how if you were doing this on a multiple choice question, you would have an idea based on the answers in the question which of the 2 options is better. So let's start by doing this implicitly, which means we're not going to solve for y. Right? So if we were to do this implicitly, what that's going to mean is that the answer will have both x's and y's. Now, if you're looking at a multiple choice question, if this is multiple choice and you look at the answers and all of the answers have only x's, then that's a hint that you might want to go ahead and do this explicitly. It might be doable to solve this for y. But if you see that a lot of the answers have x's and y's, then that's a hint that it's probably going to be an implicit problem, even though you could do this either way. So notice the left-hand side of this is a product rule. So if I do this implicitly, I'm going to get u. Derivative natural log of y is going to be 1 over y times the derivative of that stuff, which would be a dy dx, right? Plus v, which is the natural log of y, du, which will be a 2x. On the other side, I get the derivative of 7x cubed, which is a 21x squared, plus a 0, because when you differentiate the 5, you get a 0. If I now solve this for dy dx, right, I'm going to do that by subtracting this entire thing over. So I'm going to get, I have an x squared over y times this dy dx equals a 21x squared minus a 2x natural log of y, right? I would either multiply the y over and divide by x squared, which is fine, or I'm going to just multiply by y over x squared. It doesn't matter which way you do it. So I get dy dx equals a y on top of an x squared times this entire crazy mess of stuff, right? And that's just fine. If you wanted to clean it up, you could technically distribute in there, or you could leave the y out and just distribute the x, because the x squared on the bottom, because that would make this a 21 minus a 2 over x times this natural log of y. That's also fine, right? And any version of that would be fine, okay? So at that point, you're getting to the point where really your job is primarily just to match the answer, right? So you might see this answer, right? And at this point, you're just trying to match the answer to a multiple choice answer. If you did this explicitly, meaning if you instead were to solve, so if you tried to go the other direction and solve this for y, this is doable to solve for y. So if you were going to do this explicitly, the big hint that it's explicit in your answers is that you'll notice there's only x's, right? So what that means is, in this case, that you solve for y. Now, you can't always solve for y in every equation, but in this one, there's only the one y, so you actually could. If you were going to solve for y, you have x squared natural log of y equals 7x cubed plus 5. You would start by dividing everybody by this x squared, right? And you'd get the natural log of y equals 7x plus a 5x to the negative second, right? And then when you exponentiate, or you could leave that as a 5 over x squared, I suppose. If you exponentiate, which is how we get rid of natural logs, I'm going to get that this y is equal to e to the 7x plus 5 over x squared, or a 5x to the negative second, whichever you want. Now when I differentiate, I get dy dx equals, well, the derivative of e to the stuff is e to the stuff, so it's still going to have this piece, 5 over x squared, right? Times the derivative of the stuff, which would be a 7, right? Derivative of 7x is 7, minus, this will become a minus 10x to the negative third, so minus 10 over x cubed. And that's fine, okay? So that's great. Totally okay. What I want to point out to you is that these are actually the same answer. And they might not look like the same answer at first glance, but they are actually the same answer. So notice that this answer, I assure you, is actually the same answer as this. It just doesn't look the same. So either of these would be fine, right? This answer or this answer, totally fine. But if it were multiple choice, it would be about matching them. So I do just want to show you how you could use, sorry, I'm going to use what I defined y as, which is this, right? This was y. I'm going to replace all the y's in here and show you why they're the same answer. So I'm actually going to pick this one because this one's the one that looks the most like this, right? So I'm going to show you that if I replace the y's here and here, I get the same answer. So if I were to replace these y's, I get the e to the 7x plus 5 over x squared, right? That's what y is. And that's right here, so that lines up. And then on the inside, I get a 21 minus a 2 over x times, now when you take the natural log of an e expression, right, the natural log of e to some stuff is going to cancel and just give you the stuff. So I'm going to get that this is a 7x plus a 5 over x squared. So now I'm just going to clean that up, and we're going to need to go down a little bit to do that, right? So if I, oh, that's too far. All right, so if I clean this up a little bit, I still have this e to the 7x plus 5 over x squared, right? And then inside here, when I distribute this 2 over x, I'm going to have a 21, right? This negative 2 over x gets distributed to give me a negative 14x. Sorry, I'm going to leave that minus, sorry. Okay, couldn't find the eraser for a sec. So this is going to be a negative 14x over x, which we'll deal with in a sec. And then this negative 2 over x would become a negative 10 over x cubed, right? Well, that's an e to the 7x plus 5 over x squared times, this is a 21 minus a 14, which is a 7, minus a 10 over x cubed. So what I want to point out is that I was able to take this answer and turn it into the same answer that I got when I did it explicitly. So again, I don't really care which of those two ways to do it. I would probably pick implicit, but the point I want to make here is that there's often multiple ways to do the same action, and if it's a multiple choice question, sometimes the choice of method that you pick will depend a little bit on the answers that you can see, right? It's a good idea to look forward and use the answers when possible to inform your technique. That is it for Unit 3, Section 5.